yeah, and this area.
This fellow is making a lot of sound there. Kind of noise it is making.
Okay, so I'm sitting here.
అంటే ఇప్పుడు ఈ మైక్రోఫోన్ కల్లా అవుతుంది ఆ సౌండ్ మైక్రోఫోన్ ఇది మైక్రోఫోన్ ఓకే బట్ కన్వీనియంట్ ఇప్పుడు అక్కడ ఏదైనా మార్చుకోవాలంటే అంత దూరం పోవాలి కొన్ని వీడియోస్ ఉంటాయి అట్లా క్లిక్ చేయాల్సి వస్తుంది 100% దాంతో ఆపరేట్ చేయడు మీరు 10% కంటెంట్ అది అంత కన్వీనియంట్గా ఉండలేము
This
ఆపరేట్ చేస్తే
this way. Oh.
No, they are suggesting that if this microphone, that fellow is making sound. If you switch off also, that is making noise.
It's okay.
Are you able to manage like from here like this? Maybe.
Yeah, okay. Sure. I try.
Sorry for that.
No problem, yeah.
Making a lot of noise.
Yeah, but only this one is quite quiet.
Yeah. రెడ్ కనిపిస్తుంది
Okay, sure, sure. You mean standing here?
Yes,
Yeah, yes,
yes.
it's okay, yes.
Why? Because that your microphone, if you are standing there, that noise is capturing, and in the live it is.
Okay, okay,
When you
sure,
put live.
sure,
that
sure.
noise is. You okay, right? Today, huh?
I think probably, yes, probably it's time to start. So shall I start or?
Wait.
Okay.
So they are going to switch off the entire AC, the hall. That's what they are saying. That is the solution.
Yeah, shall we start? So this, good morning, everyone. This lecture is actually dedicated to the fundamental of data-driven and its application in additive manufacturing, basically simulation as well. So just want to start this lecture with these two. It's actually trying to predict not exactly the same, but trying to do something for 3D printing. One is quite high fidelity modeling, another one is more simplified. So we'll talk today about how can we actually choose or how can we make this rapid calculation for data-driven simulation, for example. So in order to start the presentation, I just want to begin with what I think we don't know much each other. So I just begin with what I'm interested in terms of research. So my research lie into, you may know, I give a lot of things on the computational material science and engineering. And then using multi-scale multi-physics modeling, this is one of the things that you saw in the past 2 days is actually related to, mostly is my research area. And then especially looking at the thermofluid dynamics of liquid metal that can apply not only to additive, but also for casting, welding, and all laser melted or molten pool dynamics here. And this is the thing that I think I'm also interested in this one, which is about the topic of today's talk. This is a digital material design. So you will see that we need to use artificial intelligence and data-driven modeling to understand what is happening in the metallurgical process. And then I want to actually working with experimentalists, especially the institute kind of experiment through synchrotron or neutron diffraction or imaging to understand the behavior of the material during the process. So it's quite fundamental understanding, not really going to the end user. But what we try to do is a fundamental for additive manufacturing that allow us to establish something more scientific-based model. So I hope I also highlight some example that we have done. So this is actually related to the model and the X-ray synchrotron published, I think, early this year in Nature.com, for example, and also understand the phenomenon happening in additive manufacturing. So physics-based model is basically something that we know is more preferable for scientific community, but probably we need to find a way to actually validate it for sure, whatever how difficult it is, but with the most delicate or more advanced technique that we can use to look at what happened. At the same time, we also want to build this knowledge in order to build a science-based data-driven platform that can enable us to get some data-driven model that established toward the material informatics for additive manufacturing. So the key words here is quite important. From the material informatics is something I will give example on last day, the final day of this short course here. And then another thing that probably benefit for someone will say about digital twin is actually we call real-time prediction for the model that we are going to give a bit information today as well in this lecture. So next one is more complicated thing. Is look to probably to me and probably to you that is not really additive anymore, but it's actually relevant in terms of fundamental understanding of chemical thermal fluid dynamics during the non-equilibrium microstructure process. And this is also give us insight into the extra information that I probably dedicated one single lecture for this probably tomorrow as well. And this is something I just want to share with you. This is a digital twin that we probably very first one to publish for metallurgical process. And this one using the, you may know, I'm not that familiar with, is a decoder or encoder for artificial intelligence or deep learning network. So what we do is actually we have direct simulation here. When I say direct, I think based on the computational fluid dynamic calculation. And then we take the images for the model to learn, and then trying to actually feed this data to replicate what happened in the model. I mean, this ran about 300 models that we can simulate. This is not additive, but this is a casting for steel. So this is doing a continuous casting in steel. And then you see that the model captured this characteristic in the in the simulation, a physics-based simulation, if you want, very well. So we hope we can develop toward this. Without any fundamental model here, we cannot actually get the reliable prediction for metallurgical process that we're interested in. So this is just something, just give you some background. But before we go into the real content of data-driven, I just want to say something about, the buzzword that people saying is data science and then big data. There are two things that should be aware of. Data science is actually for the next industrial 5.0. I believe that is a backbone for that. So it's integrated, integrative interdiscipline actually that bridge. That integrate over computer science and technology, mathematics, statistics, and knowledge-based area, which is material science or related area. So that's bring into this big picture. That means you need to work with a lot of people to make things happen. And this one also quite interesting for the characteristic of the big data. Big data is not just the data, but you need to have some, volume of data is important, small or large, or value of data. What does mean, how useful the information you have, and then how accurate and reliable. This is another important thing. What is a type of data? Is that actually systematic correction of data to get reliable prediction or not? It's not just the data that we use for just for the sake of data, but it's not like that. We need to have some knowledge-based screening of the data and then trying to put some methodological background or process engineer into that to get more prediction. And having said that, I just want to open the scene of today from this paper on the data-driven modeling of process structure property relation in metal additive manufacturing. So you may hear a lot from me that I need to link about process structure property relation. And this is really the case actually for additive to be successful. We need to link all this information together. Not only from the physical model that we are trying to do, but also digital model here as well. So in order to speed up or make it data-driven, you need to understand process, what happened in the process level, and the emerging structure. We call, if it's so small, we call microstructure, right, in micro scale. So grain size, grain orientation, grain creation. And then the property that actually resulting from this structure. So understanding of this is something we are trying to do very hard. It's not that easy to link, as you may appreciate in the last few days. But at the same time, we need to close this loop so to get optimization and design and feedback. And hopefully the data that's floating around here will be useful to develop comprehensive understanding of this process structure property relation, and then we can establish some model that can driven by the data that give comprehensive physical understanding. At the end of the day, the industry want quality control of their product, for example. So missing part at the moment is the brain for the machine learning. That as a community here, I believe you agree with me that we need to do something in order to enable some science-based or physics-based or material science or metallurgical-based knowledge for data-driven. So in order to do that, this is a conceptual diagram. But if you see for each sub-figure here, this is a data-driven for the process model. I have one example for this one in today's lecture. So what does it mean? You have simulation and experiment data feed in and with the process parameter as an input and output as a parameter that you want. So we try to make data driven for this as well. It doesn't mean only additive as an additive, but we split driven process from each component here. So for example, this one will be, probably structure modeling. That means you have process parameter and then you get microstructure evolution. Whether or not in this one you may have microstructure characterization and learn from experiment is also something we going to look at today as well. So we may have some example that looking at you have some data from experiment, especially a huge data from EBSD or microstructure characterization that we try to extract some feature, learn it, and then driven, and then try to rapidly find out or mine some things from that. Another thing is a property model, which is of interest for many people. So it's the same principle from process to property or microstructure to property. This one actually, some people may process structure and property, but again, there's many people looking at from process to property. Probably the link in the middle can be removed or whatsoever. Again, it depends on case by case, but we are trying to show you some example on this area. So, but it's still some challenge, as I mentioned before, that each process structure and property, even you do some standardization or augmentation here, and then it depends on the complete integration of the data-driven model, who will be the first one who can integrate and show. I mean, yesterday I'm trying to show some integration of cases in the fusion, laser fusion process that you see yesterday. So integration is important aspect. Deficiency and reliability of training data, and this is another thing. So you may need to have some enough data to train and test your model in order to get more reliable prediction. Another important aspect that probably is driven by methodology or engineer knowledge is interpretation of data. So actually this is the part that probably missing quite a lot in, in just data and data. That does mean data is not just data, or the uncertainty quantification. This is something we're talking about, right? It's about the what is a statistic or the distribution of the result rather than a one single point of the result, for example. And then how can we use this property structure relation to inverse design the material or the component to get the part that you want. For example, in AM probably it's more complicated, and it's probably a good example to use for this data-driven process. So just make it a little bit visualized. So we have the data-driven on the left-hand side here. So dealing with big data, machine learning, training, neural network, deep neural network, whatsoever you call it. And we have another end which you see last 2 days here. So we have defect formation, we have microstructure and Melpool mechanistic model, basically. How can we link and make these two more, talking to each other to create a digital twin for 3D printing? I think we all agree this is probably the ultimate goal for us as a community to drive the technology forward. So I give some example. This is the data-driven framework that people use. This is not actually for additive per se, but it's a kind of additive when you have the deposition of the thin film. This is for that application. So they create the data. You see this one is about distribution of some structure that they're interested in, then try to have a physics base to label or understand some feature which is important. I mean, this is just example. But the next one is actually, I think I will start with the model that we want to make it data-driven. But what I mean by that is this one. So you may know that defects in additive manufacturing is very prominent, and we need to do something on that. And defects, which is actually happen in additive, is happen in the very low scale, micro scale. Let's say this represent, approximately the scale, and then the defect, which we will discuss more tomorrow in detail in terms of the engineering understanding of that. But today we just borrow some concept of this. So we know this porosity is in the level of micrometer rather than the heat, the thermal model in finite element calculation. The size of the mesh or the grid size is actually in the millimeter scale. So there's some mismatch between the feature that we are interested in and the defect. Sorry, the calculation element and the defect content is not matched. So we cannot capture that in the FE calculation when we want to do some rapid calculation, right? So what shall we do? That is the next question. So microstructure as well is in the scale of 10 to 100 micron scale. Roughness is also in that palm scale, which is lower than 1 millimeter, I believe, apart from this residual stress or balling effect, which is actually larger than the typical mesh size for finite element calculation. But the lack of control of this, we hypothesize that is depend on the control of temperature that you have to take care of. So the key is that how can we predict the temperature accurately? So what we do, we try to propose some framework that basically try to integrate the information from the lower length scale, like the voice and the microstructure, to the larger length scale through something called more like data-driven, or someone may call reduced order model. So reduce the complexity of the model to a certain level, and then to make it more rapid calculation, and then you can find a way to scale up your problem from millimeter probably to meter scale, something like that. And this is still a conceptual. So we aim to integrate information from the interaction of the laser material and also microstructure and then resulting defect, and try to model something that you can see it moving similar to what you see in experiment. And hopefully we can establish that actually. So this is in a collaboration with some Japanese, Chinese, and also USA as well. So that is the aim. But what we do, we have to understand what we have. So in this is a normal FE or finite element model that you can do in any software, I believe now. So this is purely solving the temperature equation in a conduction mode. So the fluid flow has been ignored. So the scale that they are looking at, there is no interface tracking method at all. And this is based on finite element method on the continuum domain, with powder property is the maximum we can do. So I mentioned briefly yesterday that powder property probably important. It's efficient and suitable for part scale simulation, but missing fluid flow effect. Instead of that, this one actually thermal fluid model, and this is interface tracking method versus a flat rigid liquid gas interface. And then with or without powder packing, it still provides some insight in the scale that we want, that we mentioned earlier in the defect scale, because those porosity is a process in the defect or whatsoever microstructure or the roughness. So it's impossible for the previous model that can predict it. It's more accurate representation, I say, or prediction, but computationally expensive and limit to very few tracks. That's because it's limited by the computational resources you have. So as well, but now probably you can print about 5 to 10 layers without any issue. But anyway, the objective of this actually particular pieces of work here is to trying to build a framework for reduced order. So basically we want a clever thermal model that can take all information of the fluid flow into this some way somehow. So we try to use temperature dependent property of powder materials, and then and take into account the effect of this whatsoever by empirical means equation or analytical equation whatsoever. And then we want to predict some thermal field or history of that, and then trying to understand the thermal mechanical response. And that is the ultimate goal of this one. And this is supposed to be a data generator for our convolutional neural network that we can feed into this data set to train the data, and trying to actually learn from that, and try to establish a data-driven framework that we call reduced order model. So if we see more in detail, here we have the process material dependent absorptivity, for example, numerical implementation of the fluid flow effect, evaporation, Marangoni flow, or convection process induced porosity or micro voice here, latent heat phase transition, heat loss due to whatsoever change, phase change and radiation, natural convection. And this one is established to bridge the gap of high fidelity and the macroscopic simulation. So this is a way, actually a suggested way that we can do and learn from the high fidelity modeling. So the feature is this one. We have heat transfer, which actually, this is a relative main equation, because this is just one kind of more intelligent thermal model. There's nothing more than that. It's just a thermal model, but we try to incorporate some other physical effect on this model by looking at Gaussian heat source here. Whatever heat source you can identify here, but actually this is a volumetric heat source. It's not the surface heat source anymore. And heat loss is follow just Boltzmann kind of Einstein-Boltzmann relation. And then convection with this is normal. Heat transfer coefficients that you know and have to use a lot of time. Latent heat phase transition is actually for powder property as well. You have phase of the gas and the powder, and try to calculate or understand how actually this one is a way to incorporate the thermophysical property. It's just a model that we try to do, and then try to take into account the powder, and then take into account the fluid flow effect from the empirical relation. Again, this is not ideal, but it's something we do to basically try to take into account this into the heat model, and then try to take into account the Milankovitch convection as well in the thermal conductivity of the liquid phase here. So all this thermophysical property, latent heat phase transition, fluid flow effect has been taken into account. And now we try to test something on the two systems, on the titanium-64 and Inconel 625. And then using the property on the right-hand side, you will see that this is a temperature-dependent property, as well as titanium-64 as well from the literature identified here. It's quite big, so we don't put it here. But if you're looking at Ti-64 and Inconel 718, there will be some differences in terms of the size of the melt pool for sure, because yesterday we talked about different thermophysical property contribute to the different heat, diffusion, conduction, convection in your domain. And then if you have with and without evaporation, if you have without evaporation, that means you overestimate the temperature field, and then that means your melt pool actually bigger than the with evaporation. Again, this has to be linked some way, somehow with the lower length scale model to translate the knowledge here across, so you can probably predict something closer to experiment without any expensive calculation. And then we are looking at this as well for different system alloy that actually mostly used in additive manufacturing now, from Inconel 625, 718, aluminum alloy, and the 316 steel. And then you will see by eye, not to do anything more than that. By eye, you see that they're all different size of melt pool. Just the change in the thermophysical property. And this is, again, it's not ideal situation, because each material has different optimized process parameter, but we just show this for the sake of comparison, that you will see that, aluminum probably melt a lot, and for example. And if we try to make this one more predictive, we try to calibrate now with available data. You see that we use the mesh size quite small here, and then you see the melt pool here is actually in the size of 200 to 150 micron. And if you going back to literature from SEM, TM, or SEM optical microscope, this is in the size of the melt pool that we see in the experiment as well. So this is the dream that we want to have that quick, but not very quick, I would say, at the moment, with just a single laptop or workstation that we work on here, that we can capture some of the things that probably similar to experimental nature data. But that does mean this is one attempt that we try to study this for the dependency of the property. And one additional aspect, we can do multi-track, multi-layer AM. That means we can deposit whatever you like, but now layer 1, layer 2, layer 3, layer 4, and layer 5 here. And then you will see that the melt pool is not actually the word that we call steady state. In welding, probably you can say steady state, but this is because the heat beneath that actually contribute to the size of the melt pool for the next layer and next layer whatsoever. So there is no such a steady state in additive if we not control it very well. So this is one message from this slide. And then if we try to understand this signature of the thermal signature a little bit, we build this 1 by 1 millimeter cube here, but we can extract classic thermal signature for different layer here, for different material as well. And then what the information from this is quite useful, that I will have some example a bit later, saying that this peak temperature is important in so many ways possible that we can think of. But this is one example that we can see that, one question that we can ask from this model can tell us quickly how many layers beneath that this material has been remelting. Example, there's some characteristic that nickel probably 3 layers, but titanium probably 3 or 4, but aluminum probably 15 layers remelting every time at the optimum condition, for example. So this information also important for developing a further model as well. So we quantify this alloy dependency of the melt pool dimension as well. You will see as a bit different, apart from this aluminum, which is behaving so differently from others. And then you can characterize and get some feature that actually, CFD people trying to predict. So this melt pool size of material and process dependent, and is affect the microstructure evolution and part quality that we all know. And this has been validated against the available data at the condition investigated here. So this is a temperature field that we use from this paper here. And you will see the prediction and the measure of the melt pool doesn't make a big difference. So that means the model is reliable at some level here. So, but the next step for us, you will see the model doesn't taking into account the defect which is formed during the process yet. What is a statistical approach that we can do to approximate the defect which is formed? Because the formation of the defect during the printing also important to make the model more reliable. And then we trying to capture this based on this is simulated defect, which we will talk more tomorrow. How can we get this distribution from the CFD model? And then we try to do something in the MATLAB to generate kind of the same defect with the same distribution. So that the information translates across is statistic from the process, either from model or from experiment. And somehow you need a numerical approach to actually translate this across your calculation domain to capture. For example, this is a conceptual idea that the color bar here show red means more porosity. So somehow this will impact your residual stress and some other property. So this is probably the first step. We actually define the defect based on the data from lower length scale model or experiment, and then identify this thermophysical property that replicate the presence of this defect. In this case, it's a void small pore. So if we just prove the concept, we have only one defect here, present only one porosity here, and then we try to see the effect of this. You see this is the thing. I just see if this is a moving. Okay, no. And you see one porosity actually increase cost of computation. This is something that community needs to discuss and try to move forward. With and without pore, the peak temperature has been shifted by this. So this is something to consider for the accurate prediction of the temperature. I will have some slide talking about how important of this in a bit later. So, and the next step, once we do this and we believe this is good, so we can do data generation algorithm from that. Rapid calculation, I would say, what I showed you before. And then we generate this data combined with some understanding from the our previous CNN model here to capture this is the measure and the predicted here. We try to do the same here using the CNN architecture that we learn the data and process parameter, laser deposition pattern whatsoever, and then use some deep learning to get predicted temperature field. Again, this based on the image that you get from the result, or if you want to do like extract from the coordinate in the data is also possible, but it depends on how powerful of the code you write to make this possible. Yeah. So just summarize in the first part here is that reduce all the model, we try to bridge the macroscopic and high fidelity simulation. It's easy to actually implement in other material system. It's not just what I show you here. And we hope that the data generated from this model is a model generated data, can train CNN model that can we complete the how to say, the data-driven model here. And we hope to do the physics-based thermomechanical model that can develop to couple this with mechanical analysis. Again, there's still a lot of work to be done, but this gives you a kind of beginning of the picture for the data-driven model. But we want to do something more fancy. That is the path scale analysis, but this data-driven model also used in the Melpool length scale as well. What happens if we don't want to run the CFD now, but we just want to have the data-driven to represent what happened in CFD simulation, Melpool simulation. So this guy, I mean, in the, I think, University of Pittsburgh, proposed a framework called Computational Fluid Dynamics Imposed Finite Element Method, or CIFEM. So what it does is here is actually they try to learn from the high fidelity model using this envelope called CFD impulse zone, which actually just capture what is happening in the Melpool moment, and then try to solve the heat equation. I mean, after that, after they run the CFD, they generate the CFD using the, I think, Flow 3D, and then they generate, after they get this data, they extract this one, trying to how to say, digitalize the result, and then using the solve for the heat diffusion by Newton-Raphson method here, and then trying to deep learning FE model process. And then what they do, they get this data to train the model under the framework called CIFEM, and see how good or bad that they can predict Melpool simulation in detail without using CFD calculation. So this is what they do. So they have CFD data feeding in. This is for heat source model, and then they have encoder and decoder to predict the thermal field here. I think this based on the images, and then they use this CIFM interface to predict model thermal field as well. So the key feature is that this is just 2D transfer CFD thermal field is provided to this encoder FT that encode each 7,800 dimensional input into this 20-dimensional latent representation. And the decoder G here is denote the learn latent representation back to original input and combined network. So after that, they train the neural network model here to minimize the mean square error. Again, I think I don't need to repeat much about how neural network work. But the good things of this is actually they try to do something on additive. So this is the kind of, this is a time interval epoch loss history for training and validation. You see that it's quite good fitting both model actually for deep neural network and autoencoder here. And this used to predict the Melpool size worth of the CFD FEM used to predict the simulated Melpool size and compare with experiment. You see it's not too far off from this actually kind of Melpool size. I will show you more insight a bit later. This is a size dependent of this 20 different process parameter. So they train across these different parameter. But now another one is they want to make model more generalization. So they train this one with unseen process parameter and see how good or bad of this model is. So that means they can capture somehow, but not as good as before. But it's the accuracy of this is quite acceptable, but not ideal. And if you know, if you see here, after that, they try to understand it. As I said, this is a transient CFD impulse zone algorithm for longer scan track. So they capture, they only using adaptive match only this zone to capture this one and negate another zone. Again, this is another computational numerical technique that not many people have. So this is developed with a big company that they can do a lot of calculation here. So later they use this model to compare with different, I think this P represent different process condition, compare with the available, CFD model that they run. So you will see the differences is quite minimum from the CFD, which is heavy calculation, and the neural network calculation that they have. So CIFEM precisely. And this is what happened. And then just compare what you see. This is CFD. You see a lot of oscillation, ondulation at different conditions. This one is different condition here. And then they see with CIFEM, it's not too bad, but it's actually not the same. For sure, you can see there's some differences. And if you, ideally, you want to have something even simple, so it's just a Goldach equation here, just volumetric heat. It's actually not very good, but they capture something. But you cannot get, you don't have any depression zone, you don't have any oscillation of the things, but okay, we try to ask ourselves whether this kind of model is good enough for us to drive the technology forward. And then we compare, they compare as well, not we, they compare as well the thermal field with the size of the melt pool. Again, you will see that the CFD kind of model is probably the best match. I mean, this is the quantification of that model. You will see how good or bad, deviation of this model to each other. So that is a good step forward that they train about, I think if I remember correctly, about 800 model here or a condition. So it's a large set of data. And this is just give you an impression that the total parameter here is 13 million parameter, 13 million parameter. So contractive and auto-encoder network architecture has been used to get the result you just seen. And the deep neural network architecture here, they have a parameter about 400,000 parameter here. So it's not easy task. It has to be collaborative. It has to be something that we want to move the technology together. This is another thing which may interest to you, which is data-driven analysis. Again, this is analysis for the process structure property of Inconel 625, Inconel 718 thin wall. But this one is not pattern-based fusion, it's a direct energy deposition. But I just want to show you how they do this data-driven framework here. So what they do is actually they try to deposit the thin wall of Inconel 718 to capture all aspects from processing structure and property. And this is what they do. They have the infrared temperature measurement at different locations. So as I told you before, each location has different thermal history. So they extract this thermal model here, validate with the imaging, IR thermal imaging, and then get the analysis for the cooling rate and sulfication rate to property prediction. I will tell you what they did. They actually do predict UTS, yield stress, failure stress, modulus, based on the thermal data they get. And this is, they use the 1D convolutional neural network to extract those features. Even they can predict some primary dendrite arm spacing, which is important for the property later as well. And this is how they actually define the domain. So this is a thin wall with the infrared camera here. And then they have 3 cases, which is actually smaller build. There is no dwell time here. So that means each deposition is go on, all together, not leave some time. But case B and D is a bigger build, but one of them has the 5-second dwell time before the next deposition. This is something what you can see. And this is the model that you can see, simulation versus the experiment. You see there is some mismatch in the case C, but it still capture the trend of the thermal cycle. And why this is important? Because thermal signature here is something like this. Just one, you have some, some time between solid dust, liquid dust temperature. Just a characteristic in additive manufacturing is happen like there is no smooth curve like that. But this is what happened in real life. This is what is the complicated thermal signature, as I said. And then you can count here before it's actually solidified. There are about 5 layers that melting down the substrate. I mean, below underneath the layer. So, and then this A specimen has been carried out to compare simulated and experimental thermal history. So you will see at different location as well. So this one at different 12 and 8 location here. So what this say, actually for case B, when A, B, and C is as follow here, you see the microstructure that result from these things are different, and they have different cooling rate. As such, they get different primary arm spacing, and then they can calculate approximately the Raver's phase, which is a detrimental phase for each condition. So they can predict UTS, U stress, fraction failure stress, and also modulus here as well. So if we are looking at the specific condition on case B, which is a bigger build, 120 millimeter at 3 locations here, you see the microstructure is not the same, 1, 8, and 12 here. And then these contribute to different property set as well that they can predict here. So it's quite encouraging actually that the data from this data-driven can provide such an insight in a rapid manner. Again, you will see now data-driven is not just data. It's meaning something for the manufacturing process. That's what we want, actually. So they characterize or analyze the primary arm spacing as a function of cooling rate, because this is something, if you are metallurgy or material scientist, this will be very important aspect to understand, because this will tell you a little bit more about the defect which is formed and in the later stage. And this, actually, there's some correlation of the so many cases that they run. Again, impossible without any neural network. If you want that, we can relate the temperature, field, and mechanical property. And I will show you later that. And you will see here the temperature field or temperature, peak temperature has an influence on the property significantly. That's why we have to control this one. And then based on this scene and structure with the intermediate layer visualization here, in different conditions here, you can actually predict the UTS, compare with the CNN model, measure and predict it. And then you will see the training data is quite well, and the test data is actually not too bad, but it's not ideal as well. But at least we get something rapid, recalculate. So next one, as I promised, the data-driven model is not just the model and then finds its use. So now, if you are experimentalist here, you may question me, what is the machine learning that enable autonomous microstructure characterization in 3D printing? So this is what happened. So they try to build a model that used for real material characterization. So this is the ML method for autonomous microstructural characterization in 3D polycrystalline material. The first one is probably this image is from the correlative microscope that you get the 3D structure of this. So you first write an algorithm to identify the local structure topological classifier here, and you voxelizing the process efficiency based on the image you have, and you try to, again, these all are numerical or statistical technique that you do to basically, thresholding the boundary actually, and then clustering the algorithm and improve refinement because the boundary here is quite stepwise. So you may need to smooth out some microstructure and then optimize back to get this one for example, if this is for atomistic calculation, if you like. So this method has used to represent different crystalline material in metal. It's not just nickel-based superalloy. It's also used in the aluminum alloy FCC, iron, silicon, and also titanium as well. So you see that the size of this is quite good that they can learn and then represent the structure in 3D. And what it's used is about to get the predicted grain size with the actual grain size in the Inconel 100 nickel-based superalloy here. This is unsupervised machine learning method for the grain identification here that you can replicate the serial sectioning in experiment. Again, this is important. As I said, the microstructure is important for the property that are coming together, that away from data-driven simulation that allow you to replicate the structure quicker, faster, but minimize data storage, for example. So this one, I think, I'm a bit fast again today, but I think there's some detail that we probably need to take care of in terms of the understanding about the data-driven, and also not data-driven is not just image analysis to get something, but we need to, as a community, need to use this data-driven approach to do something which is useful or meaningful for engineering application. And I think if we go back a little bit, I just want to spend more time on this one. I think that what is the thing I want to emphasize as well is actually we said that now the in-situ monitoring is quite important. The thermal history is the backbone of the future technology. I mean, people here may have the thermal imaging things that you may see here is a temperature prediction from model and the high fidelity modeling. And these actually contribute greatly to the prediction of the defects underneath the, during the 3D printing. As you see here, this one can capture, but if you imagine if you can combine this to the way you do this one, which is in another additive manufacturing process, and then we can actually get the relationship between temperature and mechanical property. And this is a perfect scenario that we want to basically predict as a function of cooling rate, and then you will see you have the property which is actually has a correlation, I would say, or have a correlation with the UTS, and this is the ultimate aim that we want to get. Another aspect that I want to emphasize is that there is stochastic process. So we're trying to predict the trend at a statistic, the distribution, and also the noise of the process that we want to reduce as much as possible to control it. So the way forward is to control the the noises in the system that can allow us to do the quality control of additive manufacturing for specific material, machine, and process condition we want. I think probably I want to open for discussion now. If you want to ask anything regarding this, yes, please. Otherwise, I may have to have another. Yeah.
So I would just want to ask, with evaporation there will be evaporation. During the evaporation there will be vaporization of the element. Okay, they will take away the heat from the manifold. So will there be reduction of the temperature of the high peak temperature of the manifold as well?
Yeah. When evaporation, evaporation here kick in, because if you have the normal diffusion, thermal diffusion equation, when you solve it, it can go to the ridiculous number like 10,000 degrees centigrade, and this is not realistic, because nature not allow this to happen. Because once you get to the boiling temperature, there will be some dissipation of the thing. So the temperature usually never go up to the boiling temperature. So we damp that temperature down due to the, what is called, due to the latent heat that we need to damp the temperature down. That's why the heat contained in the material actually lower, and that means once the energy here is lower, the size of molecule is smaller. Your question is?
Sir, in this case, in the legends that we are seeing over here,
Yeah.
the legends, the peak temperature is somewhere around 3200 Kelvin, 3200 Kelvin, both these legends, with and without evaporation.
Without, it's about 3,000 Kelvin, which is around the boiling temperature.
I'm just asking whether the temperature will also, peak temperature will also reduce in case of evaporation, when we consider the effect of evaporation.
Yes, if we consider evaporation, peak temperature will be reduced.
Reduced. Okay.
Yes.
So, but there.
Previously, it's overestimate. If you don't corroborate evaporation term, this will be overestimate your temperature.
But there, what in the legends it was shown that in both the cases the peak temperature was near about 3200 Kelvin.
Which one?
Back slide, previous slide, please. Previous slide. More. Yes, over here. Yes, over here. In both the cases, the legend, as per the legend, it shows that the temperature is
Okay.
3200 Kelvin in both the legends.
Okay, okay, how to read it? This is something to be careful. So that means that the top one is actually blue, right?
Yeah.
That means any temperature above this one is also blue as well. So this doesn't show absolute value here. It just represents that temperature above 3,000 something, it will be blue, and then you see the blue region here is larger than this one.
But the legend would have scaled as per the highest.
Yeah, sure. That's correct. But it is actually around something ridiculous number like 10,000.
Okay. One more thing. So you have discussed this thing like using deep learning architecture, CNN, and other things with this CFD model, right? In some slides. So how can we incorporate physics-based loss function within the means what kind of physics in case of welding analysis or laser powder bed fusion we should consider to incorporate physics-based loss function within our deep neural architecture, means CNN architecture or something like that. Physics-based loss function. Typically we use means already available from TensorFlow or Keras. We use loss functions such as
I'm not sure I'm not sure understand your question correctly. But
so
if I'm trying to answer your question, I understand that you're asking me how can we incorporate the physics based loss
functions
in the machine learning. So what I show you, probably the next example, is actually we learn the data from physics-based model.
Yes.
You understand? So it's basically image analysis, just image analytics. Yeah. So that's what it is. So that means that result contain physics already. But if you ask me in another, probably not in this case, if it's actually applied to some, for example, alloy design using data-driven as well. So you may need to have a kind of equation to incorporate the physics into that. Again, that is not applied in the example I show you. It's just that learning from the data generated from high fidelity model in this case, yeah. Otherwise, you have to find a kind of a numerical framework that incorporate the lower length scale information to the large length scale like this to get the rapid calculation for the model. Again, this already taken into account physics, which happen. So it's number of ways to do that, but I think your question doesn't apply to my talk
So,
at the moment. Yeah.
okay, but it typically people are working on physics-based this deep learning architecture where they use Navier-Stokes based loss functions into their model.
Yes,
Yeah.
that is another. I understand that, but that means they want to run separately the model with the taking into account the physics base whatsoever. There, that's also a way to do or generate the data as well.
And one more thing, you had shown that Golduck volumetric heat source,
Yes.
it was not able to predict the temperature fields much better compared to the CFD based model, right?
Yeah.
So if in case if we replace
mean
the Golduck
Golduck? Yeah.
volumetric heat source,
Yeah.
if we replace it entirely with the conical heat source distribution, volumetric heat source distribution,
Yeah.
so
In
that
principle, we
might
can,
be comparable, I guess, right? Means I
we,
just
we
want
can
to
try. I also but I believe they also try as well. But probably this is the best match. I mean, analytical equation that match. But it's not ideal, as you know. This is if I want to comment on that work, that means they do only one track, right? What happens if you do 2 track, 3 track? This will be different again. You see, and I'm pretty sure analytical solution cannot capture that.
No, I'm not talking about the
Yeah.
analytical solution. I'm
But
just
you asked me if we compare with different heat source model. That's what you asked.
heat source model,
Yeah,
just
yeah.
heat source distribution that is being incorporated
I
into.
think probably a good trial if we can come up with or using the learning to come up with a new heat source model that represents this data. That would be a good idea forward, I think.
Okay.
That means we only deal with one equation, right? That we can use for simulation, rapid calculation. That's what your question, I
No,
believe.
actually, I was not asking about the analytical solution. I was asking whether in their case they have included Golduck heat source or volumetric heat source within
No.
the file. Huh?
No.
They haven't
What
used.
does this mean? Include? They just use that to compare under condition that they simulate with the CI, FEM, and then CFD. Because that is basically the equation, right? That I show you.
Okay. Okay,
I'm
thank
not
you.
sure.
Okay, I will ask you later. Okay, thank you.
Thank you. I understand this is the one you asked, right? Why you said why it has to be this one or?
Actually, they are using Golduck heat source model, right?
Yes.
So in that case, if we are going to use conical heat source distribution,
Yeah, you can.
it can be comparable. It could be comparable to CFD, right? With CFD result. In some sense, if we just want to compare the thermal.
Yeah, of course. You can have another column here with another conical heat source also and see if how comparable. That's what your question, right? Yeah, sure. Thank you. Yes, please. Yes.
Can you please explain a bit more about the reverse engineering part?
Say again.
Reverse engineering part, like there was a one slide, right? In the previous slide. Reverse engineering.
This reverse engineering one. What is the
Yeah, next one.
this one?
Even that.
Back. Very first slide.
This one, next slide. Yeah.
Okay. Yeah. What your question?
Can you please explain a bit more? Can you please explain a bit more, like how it's working and all?
Yes, I
To elaborate.
yeah. So just want to show that they have the inward and forward design. As you know, it's probably better to make it look probably this one is the same thing. So basically you have this is a forward design, right? Straightforward from process, structure, and property, and inverse is just from property that you can decide what is the process that what is the property that you want that process condition that will produce that. So you reverse inverse your design here. I just showed an example here that this is the target performance that they want. So they inverse design from the target performance or property here, and then they try to decide what is the condition that they need to make it. So it's the same as my very, very, very first slide on saying on additive that we need to understand the process to design this one. So, but basically this framework has been used for thin film material here. So just this is my point, that's it. Yeah, so basically from this one, not only additive, other people also doing the same as well. But as I said, I want you to appreciate that this is whether or not they get some synthetic microstructure here and then doing some learning here. I think in terms of the principle is pretty much similar, but the details are so different because we are looking at different probably feature, property, or whatsoever. Yeah, thank you.
I just want to know how the physics is captured in all these models, whether it is like using the PINS model, like physics-informed neural network, or some analytical models in capturing the physics of all these from the microstructure level to the property correlation, structure property correlation.
You mean if we use the machine learning based model, right?
Yeah, physics-informed neural network or something like which includes the physics last term to capture the physics-based
yeah, it's
approach.
probably a similar question as you. I think from here it is learning from the result from the model, from the high fidelity model. But if you want to have the physics-informed neural network, it's probably applied to, for example, alloy design, another thing. So that means one of the way we do it, we use the inform it from experiment. That means you may extract some empirical equation, simple, one line, feeding into the neural network algorithm, or you extract the relation from, let's say fluid flow from model, again, simple analytical or one equation into that. That is how I see that people do the linkage as well with the physics, or we call physics-informed model. And that means before that, you may need to use some knowledge from material or engineering to screen the data. So the data is not just the data. If you have 1 million of data, we need to find, knowledge-based screening and then clustering before you training and blah, blah, blah. I think tomorrow we'll have an example that they show in some cases we have to cluster between different set of data. Let's say this belong to one grain or this belong to another grain, for example, in the microstructure level. And it's a combination. Definitely, that will make your neural network or machine learning more clever, right? And this also apply in our alloy design algorithm as well, that we use some methodological understanding to inform the data-driven model that we show on Friday. So yeah, in short, deduce your relation from experiment or the model with a simple explanation, feed into the neural network. Again, this will increase your calculation time probably significantly in the neural network, but it is probably worth doing that. With the assistance of the computer scientist, we may try to make it quicker. Yeah, but anyway, that's probably your question, right? Sure.
Sir, can you go to that can you go to the melt pool thickness slides? The comparison of some 5 different materials you have shown. This one, sir.
Yeah.
So here we use constant power and laser speed for all different materials.
Yeah.
But
this is for the sake of comparison.
But in reality, if you take aluminum, that is a low melting point material,
Yeah.
obviously we'll choose lower power. So
Yeah.
in that case, if we keep higher power, Inconel, it's obviously high melting point material
Yes.
as compared to aluminum. So definitely.
Understood. Yeah.
So then how representative these models are like? is it okay to compare with this same laser power and
Understood. So that's why I said at the beginning that this is just for the purpose of comparison. But in reality, we need to optimize. We need to select optimized condition for each material to simulate. But for demonstrating the thermophysical property dependency of this process, just for visualization, this is what we see. And then I appreciate that these three have the similar kind of melting solid at liquid at temperature, but not this one. But yeah, you are right, completely correct. But this is just for comparison. Yeah. Yes, please.
Or have the data. So usually we go for those high fidelity tests. But they are also based on some physical model which have some assumptions. And they are usually they are away from
So
the
you said high fidelity model.
Yeah.
What is a high fidelity model different from physical based model? What is
No, they are the same.
Yeah,
They are the same.
Yeah.
And we usually take data generated from them to train our data.
Yes.
The data driven models.
Yeah.
But usually they are away from the reality or from the experimental data.
Yes.
So usually we get asked this question that why didn't we use the experimental data to train our model, data-driven model. So what is your take on that? How do you answer this question, or how do we?
I think this is a very good question. But in my opinion, it depends on what you are looking for.
Yes.
Let's say if you are looking for microstructure prediction, for example, definitely, probably at the moment, only the data from experiment which we generate a lot can be more reliable to use for the training, which is true. We have evidence that. But the problem of this is that if you collect this data from different conditions, different places, they may get some, how to say, inaccurate.
They have biases
because
there.
Bias.
Yeah.
So it's actually not systematic correction. This is another question, whether you can get a systematic data that we can use for reliable prediction. This is the question. But modeling definitely is more systematic in the sense that you know what to do, right? And then you start generating tons of data, given your resources around, for example. And again, there's this something that we need to work together to make the prediction from the model closer, because that means you will remove the necessity to do experiment. And that is the goal, right? We don't want to do expensive experiment for some expensive material. We're trying to make the model as intelligent as possible to do that. And that is the goal. So I hope not too far from now, we can get that point. In some cases, we can show that probably model data can have predictive capability. But another aspect of modeling that can provide you is to predict some feature which is difficult to experimentally measure, like fluid flow pattern, for example.
Thermal history is also difficult to measure experimentally. In situ.
Yeah. But some cases, if it's not in this metallurgy field, it will be in CFD, for example, fluid flow in the flow of the airplane, something like that. So that is something not easy to measure, right? But if you can find a way to rapidly calculate without doing direct simulation, that would be good. So again, my answer to it depends on which application and what you want to do.
Thank you.
Yeah, here.
Sir, while modeling the thermophysical properties, so we use standard data, right? So that are taken at a standard rate of temperature.
Exactly.
But when it comes to additive manufacturing, the rate of heating and cooling is so high. So are we considering the kinetics while taking the thermophysical properties?
Very good question. I think this is another area of research as well, thermophysical property. So That's correct, because we rely on what we have at the moment, right? And then we try to do something about it using some, we believe we're using some kind of this, what I told you before, so fraction of the powder, and then you believe that this is the bulk and the powder property will be following that. Again, this is assumption. So we don't know whether this is correct or not, but we hope from the previous understanding, this assumption actually better than just using the bulk property, for example. Again, the bulk property here is actually come from different metallurgical process. You will know there's some differences, and these differences may be important to the predicted peak temperature. Again, hasn't been very fully investigated yet, but there's some commercial software packages trying to make some new database for AM or powder, basically. I think you know about that. So yeah, I think this is something to research and do more. It has to be experiment, because this is something. Otherwise, you have to run first principle calculation, quantum mechanics kind of model to get this, but it's not ideal to do it because it's so expensive as well. Thank you.
Any other question?
Yes, please. Yeah.
Sir, you mentioned that one, finite element methods, continuum application, continuum mechanics, that one. So is there any case study on that also? Just continuously we have a
Which one you said?
finite element method properties, material properties. One slide was there. FEM.
This
no,
one.
other one. So one slide you have mentioned that one state in the initial
In
starting. FEM based analysis.
this one? Oh no. Oh, okay. This one. No, the next one, right?
Initial. Starting like.
No, this is the one
In the one
analysis.
statement you have mentioned in the initial slide, starting classes, like that FEM one case study, you have one elaborate explanation on that.
Okay, let me go to that one. So we understand the same thing. This
Next
one.
No, FEM statement is there in the data also.
Which one actually?
Let me, I'll show you, sir. In the
This is the first slide.
next.
Next one. This is my.
Next. Okay, I will show you, sir. It is there in the book. One finite element method on continuum material desired properties.
Yes. Anyway, can you ask your question? Yeah.
And how do we catch that weld pool size while printing? Exactly that whatever you have shown the weld pool size numerical model. So while printing, that weld pool, whatever laser speed and temperature, and we can capture it. That weld pool, whatever the size is there, 210 microns, you mentioned. So how can we accurately calculate that one, sir? Experimental. Is it possible?
Yeah, there's a lot. I mean, yesterday I showed you the measurement of the temperature that people trying to measure the size of the melt pool on fly. That's mean doing the deposition. And that's what your question, right? How can we accurately capture?
Yeah.
This is another research for institute kind of monitoring people. So they're trying to find a way, because they said the infrared information is probably somewhat over or underestimate the melt pool boundary. I think this is the technique that related to the instrumental things. Again, I think, as far as I understand, they try to use different kind of way to capture it. Whether you use thermocouple, which is very more reliable for engineer, right, to validate against. But it's impossible because this is a melting process, and it is, yeah. So the way forward, as far as I understand, I don't know much about this area, but my colleague does, which is from Imperial. He will try to find a way from the changing the heat source as well, or camera as well. So they have different model of camera that I can't remember exactly, but that is to interpret the emissivity from the camera to get better representation of the temperature. But still, some people in some lab also quite reluctant to say this is a temperature. They just say that this is the melt pool boundary. Don't talk about, but that probably enough for us to move forward, because the melt pool size is important for microstructure and other things development. And then you can say that if you know melt pool boundary good enough, again, this related also to the resolution of the camera. What is the spatial resolution, right? If it's so rough, so coarse resolution, you won't be able to define the boundary clearly. And anyway, this melt pool information will be important for microstructure and property later. So this is what I see. So in short, that means instrumental or in situ monitoring system may need to be implemented, make it more reliable for us as well as a modeler. We need reliable experimental data to calibrate, to validate with. Yeah. So yeah, that is something that people in this area may need to do experimentally. Yeah. Yeah. So we did it in a number of ways. For example, we are looking at previously, before we show here, we use thermocouple at the substrate of the material. One thing. Second one, we use synchrotron imaging. Again, synchrotron people, even they know in the melt pool length scale. Now you are zooming in the melt pool length scale. They still reluctant to summarize that this is the temperature that you get, but they later said this is the emissivity profile that you get. So like that. So I mean, this is a way to represent thermal field, but we cannot probably say for 100% sure this is the 1555, something like that. But just a qualitative measurement at the moment, as far as I know. But someone tried to claim as well that this is the temperature, but it's based on assumption anyway. Yeah, that represents what happened. Yeah. Yeah.
Professor, would you please go to the thermal signatures slide?
Say again?
Thermal signatures. Not this one. Next one. Yeah, this one. Back one.
Oh, this one.
Yeah.
Okay.
So this is a simulated thermal profile.
Simulated.
Simulated one.
Nothing doing with experiment at the moment. This slide, yeah.
Yeah. So how to accurately get these thermal signatures, simulated ones, in comparison with the experimental thermal profiles? When we see the experimental thermal profiles, the pattern is slightly different, and this seems to be an overestimate of the temperatures, right? In the layer 2, layer 3, layer 4, if you go, the temperature is increasing, whereas the general trend is it decreases.
Okay, I need to tell you, we are sitting at the same position when we measure the temperature. Yeah. That means this position experience, that means this one, I'm staying at point A here.
Yeah.
I'm still here, even they have the second layer.
Right.
That means this temperature experience lower temperature when you pass. Whether or not this will be remelting of, you see, I'm not following the path. I just stay, let's say, at the base of the material.
I agree. My question is, I understand the peaks A, B, C, D, E.
Yeah.
The temperatures go down as we go to the next layer at the same point.
That's we are at the same point.
But the baseline temperature, the baseline temperature, the trend is in an increasing mode, whereas in reality it is a decreasing mode.
Understood.
Then we get an overestimate of the temperature, is what I feel.
Understood. I think you spot the right point. Yeah. So I agree with you.
So what is the parameter we need to change here so that we get the realistic trend more?
I think what we are looking at is probably transfer coefficient at the substrate that maybe suck some heat out of the domain. But again, this is still need to be improved. As I said, we try to develop a framework using those empirical relation here or from modeling here to basically show the proof of concept what we have. But anyway, you are correct. Yeah, it's expected to be like this, even it's slowing down, like I show in schematic diagram. Yes, sure. It's also contribute to that as well. You mean the well time, I mean, leave some time before deposit the next. That's also what we consider. Yeah. Again, this has to go hand in hand with experimental list to see what is the real representation for the situation.
Yeah.
Agree. Completely agree. I think his point is this, actually. This is why this is a little bit increased here. Yeah, but he said that in reality, probably I mean, in order to capture what really happened, I also agree with you as well, that under assumption made, this is correct, but in reality, if you compare, it will be this kind of temperature. It will increase first, actually, and then decrease, right? This is a measurement, experiment here. It will increase first and then decreasing. This is from experiment. But again, how you trust this IR imaging, this is another question. Yeah, so this is increased first, and I understand, and he also correct. Yeah. No. Yeah, but you see here, first few layer is increasing. Again, I said after that, we need to calibrate with experiment carefully. So nothing wrong with the model as well, but we under assumption made is correct based on that. But yeah, thank you so much. Any other question? I think I like the session like this, that we generate some discussion and then.
For the better understanding of each other, can you please, in a quick way, so what you are doing here?
Yeah, introduce yourself. I don't know. Yeah, okay. I am experimentalist looking at instrumental whatsoever for male pool, something like that, or you are metallurgist looking at the alloy development. That would be great.
I'm a mechanical guy.
Yeah.
I'm not a metallurgist either, nor a metal scientist. So definitely the perception which it will vary.
Yeah.
For the better understanding of each other, so may I request in 1 or 2 minutes quickly, so yeah, introduce your work, so better you can understand.
Yeah. Who? So in the meantime, just want to say that in the next 3 hours, I mean not 3 hours, more than 4 hours, right? So next two sessions will be about the training from my postdoc. He will join online. I don't know much in detail how to do setup and everything. He aimed to show 6 cases for the ANSYS fluent that we implement for additive manufacturing. So please do ask if you have questions, but we aim not to go over the scheduled time because we have other activity as well. Yeah. So probably 3 cases each session. Yes. Yes.
Sir, good morning, sir. Myself Swaminathan. So I'm.
Where are you from and what are you doing?
Yes. So I'm an assistant professor working in PSG, Institute of Technology and Applied Research, Coimbatore.
Yes.
Sir, recently we started working in the area of metal additive manufacturing. So
metallurgy.
Metal additive manufacturing.
Right.
I'm basically
which material system you are looking at?
Yes, sir. One is aluminum silicon 10 mg.
Right.
So in which using thermal imaging system,
okay, you are
we are trying to powder bed, sir.
Okay.
Powder bed. So we try to using data-driven model. We are trying to address the porosity related issues. So we try to optimize the process parameters based on the porosity, minimization of porosity, using thermal imaging analysis type.
Right.
So that is one part of work we are working. We just started working.
Right.
And the other work, which is basically modification of in-kernel based powders by adding yttria and yttria stabilized zirconium.
Which ink canal you are?
718, IN 718. We do.
You know, there's someone in Sweden also doing similar thing. I think with the changing some. I can't remember some element.
Yes.
Vary percentage, and you want to check the printability of that, right?
Yes. So it is similar to that. People they do some coating of yttria on in-kernel. So what we are trying to do is instead of coating, we'd like to impinge the yttria at a nano level on the surface of the in-kernel powder. So we use that as a raw material for additive manufacturing, and we'd like to see how the material behaves, how the corrosion property. We are planning to do these kind of studies. So currently we successfully able to produce the powders with surface
Very
modification.
Very
So
good.
next step we are planning to go for
Printing.
additive manufacturing. Print.
Yes, sure.
Yes.
Anybody from IT Madras?
I'm Sriram and I am from IIT Madras. And this is my first semester and I am PhD scholar at Department of Engineering Design. And I'm doing my coursework currently. Currently, my professor has given the topic on the fatigue life prediction of the additive manufactured components.
Fatigue life
prediction. So using the fracture mechanics approach and
Very
defect
difficult,
modeling, like
yeah.
the pores, lack of fusion, and keyhole formation in the additive manufactured components. And I aim to model these defects and how it is going to affect the fatigue life of the component.
Okay. What is the fracture mechanics framework that you use for your fatigue life prediction?
No, I have to do some more literature review on that. So
Okay.
this is just my coursework.
Okay, sure.
Good morning, sir. Myself, Maurya. I'm Master's Research Scholar at IIT Madras from Engineering Design Department. I am working on developing digital twin for autonomous factory, which involves a 3D printer as well FDM printer. So I'm trying to predict defects from the data-driven and physics-driven modeling of the FDM printer, so that it is helping us to identify defects within the factory setup and give a control feedback to the machine to rectify them in real time. So that's what I'm actually working on.
Very good. So you said automation or
Autonomous factory.
That mean will be robot.
Yeah, robots are 3D
So it will be
printers.
DD process,
Yeah.
right?
Yeah,
Direct
like-
energy deposition.
No,
Why
like in our factory setup, we have multiple things. Like we have a 3D printer, 6-axis robot, CNC machines, and all. Like
Okay,
we
sure,
have a
sure,
test
sure.
bed of factory setup, and out of it, I am
Okay.
working on the 3D printer digital twin
Sure,
development.
sure. Thank you.
Just want to add a point, like mine would not be related to physics-based and data-driven modeling for the remaining life, RUL, remaining useful life prediction for the component.
Thank you.
Hello, my name is Saurabh Tripathi. I am a PhD scholar at IIT Kharagpur and I am working under
Kharagpur.
Professor C.S. Kumar. So in our lab, basically we have EOS M290 with in-situ monitoring setup. Actually, we had this machine since 2009. And
Right.
earlier, we were actually in this entire country, India, we were the first one to have this machine, and that too because of one of the visionary professors.
2009 you're talking now.
No, it was earlier 270, and one of these research scholar actually he had mistakenly damaged this machine because he was trying to process copper. So
Yeah, challenging material.
yes, so it was very reflective, and it got entirely that laser system is down. So we have kept it in our separate lab that still
Yeah.
US people
I
haven't
suggest
picked
you
it up.
use the same technique as him, coating the powder, but anyway, later.
So later, currently that guy is currently professor at IIT Delhi. So in our lab, earlier people used to do a lot of experimental stuff like surface re-engineering using the same, because the chamber itself is having a controlled environment, so it allows them to do various kinds of stuff. I have been this before me. There was one more guy. He started doing this thermomechanical modeling and stuff. I picked up. I'm not parallel to it.
Tungsten, you said.
So I picked up separately, and I was really fascinated because I was when I do the literature search, I was actually following your papers.
Oh, thank you very much.
So that was the real inspiration that I came here, because I was working. I had worked a lot in thermomechanical modeling.
Yes.
But and also DM methods and all those things.
Sure.
But recently I have also started to more look upon to CFD models as well, because multiple physics is not able to properly capture in the FM model. However, the FM model is more suitable for macro modeling and all those purposes. But
very
still,
good.
We are also having earlier we used to do DED setup in our metallurgical department. There was one setup. In our mechanical department, there is another setup. It used to be open environment. There was not, so there was chances of oxidation and all those things.
Yeah.
But recently we got Optomac, so it's kind of hybrid system.
Sure.
So
DD with machining.
And this is not only this stuff. Actually, I am the only person working in this. In my lab, people are basically working in FIB, SEM, nanoscale printing, and my professor is more controls guy. So his field is entirely different. Means like underwater robotics and all those things. So it is entirely very diverse.
Diverse.
Diverse
Very good.
thing.
Yeah, that's why. Or probably we can.
Hello, sir. Good morning.
Yes.
My name is Misbah, and I'm PhD scholar from IIT Jodhpur, and I work in the field of metal additive manufacturing, basically in DED.
Right.
And my work currently is mostly on the experimental part, wherein I'm studying the composition control during additive manufacturing. So now
composition control.
Yeah, during actually
just published one paper on the composition
recently
change.
I went through that paper with I think Professor Tohin Mukherjee. I studied that, and that's the way I actually want to proceed in my work. Like get into data with modeling, computational modeling. So these things are what I plan to include in my work. So that was the basic force to join this workshop to know more about those things.
Good. Thank you very much for coming. Sorry.
Myself, Rakesh Kumar. I am from IIT Ropar, and recently I have completed my PhD.
Computer department or
mechanical department.
Mechanical department,
I completed my PhD in the biomaterials.
Biomaterials, wow.
And currently I am working with process simulation, like multi-physics process simulation for single track and multi-track. Using both approaches like analytical and numerical. For numerical, I am using like COMSOL.
Which material you are looking at? Biomaterial, you said?
Titanium, TS6L.
Oh, okay. It's still metal. Yeah, okay.
Metal only.
I was thinking you're talking about tissue.
No, not metallic biomaterials.
Okay.
And we have used developed some model to predict the melt pool characteristics using thermal approaches and fluid flow, incorporating the Marangoni and recoil pressure.
Okay.
And apart from that, right now I've just started to process in the simulation itself multi-material to process multi-material during the process itself.
I'm interested in that multi-material.
I'm also looking for a postdoc, so
okay.
we can talk. Thank you.
Thank you.
I'm Ramesh Kumar from IIT Tirupati. I am working on electroplasma polishing of thin wall structures, which are 3D printed. So that's why they are also
thin wall structure using LPBF or?
No, power bed fusion. We have EOS M290 mission.
Okay.
Powder bed. So whatever the printed structures having that lot of porosity, like surface roughness is very high.
Which material you are?
Steel 316.
Steel 316.
We are in a developing stage only. Recently we purchased, IIT Tirupati purchased that mission. So So there also we are applying the voltage 280 to 300 degree voltage in electroplasma polishing. Same pool will generate. So we want to study on that water plasma generation. So and a sustainable solution we are generating one solve solution. So
very good. Yeah, very good.
EOS M290. 290.
ASM. Okay. Yes. We probably can continue after. Yeah.
Maybe some scientists we can.
Okay, sure.
We'll listen from him. He's a scientist.
Okay. I think we should have done this at the beginning.
Yeah, Professor. Professor, as I interacted with you, we are from Defense Metallurgical Research Laboratory,
yes,
where we are working on this powder bed fusion and DAD for the past 5 years. So we have been printing specimens, components, and doing a lot of characterization, generating the data. Now we are just recently entering into the molding aspects of this LPVF, doing the single track, multi-track, multi-layer simulation. That's where I got stuck up with multi-layer simulation. It's not easy to do. It's very complex, as you have been mentioning for a long time.
But now it's a lot easier than before. Yeah.
Yeah. So basically, our idea is to understand the melt pool dimensions and the temperature history, so that we can optimize the process parameters for the existing alloys, conventional alloys like maraging steel, Ti64, aluminum alloys, and also some novel alloys for futuristic materials and all. Let's say we are also looking at the optimization of parameters for the tungsten alloy.
Yes,
tungsten.
That's also something I'm interested in.
Tungsten-based alloys.
High temperature refractory material.
Exactly. So we are looking at this molding and simulation on LPBF and DED also, basically for the optimization of process parameters.